Okay, so in section 5.7, what we have here, hold on class, let me get my little pen out here. This is absolutely fascinating. What we have is a linear system of differential equations. A linear system of differential equations. Okay, so, you're used to seeing one differential equation and solving it, right? How many remember separation of variables techniques, for instance, from Calculus 2 to solve a differential equation? It doesn't work all the time, but how many recall that? Or maybe okay, so all right, Naima remembers it, Nafani remembers it, Justin, yeah. Well, what if you had a linear system of differential equations? I mean, here you have x1 prime equals a11 times x1 plus a12 times x2 plus all the way up to a1n times xn. Okay, and then you have x2 prime, x3 prime, x4 prime, xn prime. Okay, you have it's called a linear system of differential equations. So this comes up, for instance, like in engineering, you could have a circuit, for instance, where the two differential equations represent the derivative of a current and voltage, the vector. So, well, let me just say, so this comes up, okay, this comes up, and this linear system of differential equations, we want to represent it in a succinct way. Well, I can represent that linear system of differential equations as a matrix equation, where on the left-hand side I have the vector x prime of t, and that equals on the right side a times x of t, where xt, x prime of t, that vector, and the matrix A are defined as you see them there. And here's again where your knowledge of matrix multiplication, your knowledge of the row column rule, really helps you see that a times x of t would give you the right-hand side of all those differential equations at the top. Is everybody, I mean, are there any questions on the notation here? Are there any questions on the notation that you see in front of you? Okay, and incidentally, how many remember how, and again, an example where you could have a system of linear system of differential equations, if you had a circuit, you'll see this in your homework. You don't have to know engineering for this, but you can have a system where your derivative vector consists of the derivative of current through an inductor, and then the vector on the left would have derivative of current through, the entries would be derivative of current through an inductor and the derivative of a voltage drop across a capacitor. Okay, how many have maybe seen inductors and capacitors in maybe in a class before? Okay, in electronics, Justin's seen it, and who else has maybe seen that in a class? Kirchhoff's law. All right, Lewis has seen it, and Justin and Benjamin, and some of you will see it. But that's just like one example. Okay, but okay, well, all right. So we want to know how can we solve for x of t? I mean, the vector x of t that consists of x1 of t all the way to xn of t, those are the solutions to the linear system of differential equations. And we want to know, how are we going to solve, how are we going to find those solutions? Okay, and this is something that if you've taken differential equations, Math 282, you would have seen what I'm going to show you at the towards the end of the course. How many maybe recall eigenvectors and eigenvalues being used for linear systems of differential equations in 282? If you've taken differential equations, 282. Okay, Justin, Benjamin, and in that class, you just sort of were told, okay, this is true, accept it, because but now that you're taking linear algebra, you're going to know why what I'm showing you is true and what you learned was true. So on that note, let me go ahead and bring up whoops, hold on, I want to share a file here. Okay, discussion problem. All right, let me give you a moment to copy this down. And I want to mention, class, in your notes, whenever you see bold symbols in your notes, you should be, putting vector symbols in your notes, right? So x of t is bold, the x is bold, the eigenvector v, it's bold, so it's a vector. So it'll help you tremendously. I mean, you should be putting vector symbols, right, in your notes. Okay, let me give you a moment to copy this example down. Okay, so let's take a look here. So we're going to let lambda be an eigenvalue of a matrix A, and we're going to let the vector v be its corresponding eigenvector of A. Okay, and remember, the eigenvector v has numbers in it. There's no variable t in the eigenvector v. What we want to do, so just like in differential equations, whether I mean, everybody had it in calculus 2, a little bit of it, and then if you take Math 282, you'll see a lot more of it, of differential equations. But we're always interested in, how do you solve the differential equation? What's the solution going to look like? Well, here we want to know, what does the solution to a linear system of differential equations look like? It turns out that something called the eigenfunction will be a solution. The eigenfunction is given by x of t equals the eigenvector v times the function e to the lambda t. It turns out that this, and that's called an eigenfunction. If you take an eigenvector and multiply it by e to the power lambda t, where lambda is the corresponding eigenvalue to the eigenvector, that's called an eigenfunction. And it turns out that an eigenfunction is a solution to the linear system of differential equations. Okay, how many would like to see that proved? Oh, I thought I'd see a lot of hands pop up here. Okay, thank you, Eleanor. Thank you, Nafani. Thank you, Justin. I agree. Let's do it. All right. May I go to the next page? Does everybody have this copied okay? Okay. Here's the proof. It's not hard. It's not hard. So what I do is I say, all right. So x prime of t, by definition, is the derivative of x of t, right? So I'm taking the derivative of a vector. And when you take the derivative of a vector, you take the derivative of each of the components of the vector. But remember, the vector v is an eigenvector and it has constants in it. So constants can be pulled out in front of the derivative. So you can actually pull that eigenvector out in front of the derivative. And so you're left with the eigenvector v times d dt of e to the lambda t. Well, you know how to take the derivative of e to the lambda t. Just use the chain rule. That'll equal lambda times e to the lambda t. That gets me down to here. But v times lambda, I can write as lambda times v, of course. But what is lambda times v? Lambda times v is just equal to a times v because lambda is an eigenvalue and v is the corresponding eigenvector. So you end up actually here, I'm going to put some parentheses right here. You end up getting that x prime of t equals a times x of t, right? So if x of t is a vector of functions such that x prime of t equals a times x of t, again, if you have an x of t vector, that a vector of functions such that x prime of t is equal to a times x of t, then that vector of functions, in this case eigenvector times e to the lambda t, that vector of functions is a solution to the differential equation. In other words, well, yeah, it worked. And therefore, now you have a solution. And what I did on the right side here, I'll just mention this. These steps that you see here, okay, I try to justify them with just a nice little example. This example here doesn't it's just an example to help you feel comfortable with things. So like for instance, okay, why can I go from the derivative of v times, why can I pull out an eigenvector? Okay, I'm not used to pulling out an eigenvector from a derivative. I'm used to pulling out a constant from a derivative. I'm not used to pulling out a constant vector from a derivative. But if you look here on the right, I start off with the derivative of a vector v times e to the 2t, and then e to the 2t, that's just a scalar. It's a function, but the function multiplies each component. And then I can write each component as you see here. Well, I want to be careful. No, I write the eigenvector v, the vector v times e to the 2t. I write it as you see here on the second step in the example by multiplying through the components of the vector by e to the 2t. And then I differentiate the vector. So in the third step, I differentiate the vector. Well, differentiating a vector is the same as differentiating each component function of the vector. And now what I can do is I can write this vector here as this final vector, and the vector v times the derivative of e to the lambda t. And so then you should feel comfortable going from here to here. That's why I wanted to do this here on the right, to help you feel comfortable from going from this first step here to this second step. After that, I think the steps are pretty clear. Is this example helpful on the right? Does this? I was debating whether to put it in or not. Do you find it helpful in feeling comfortable in the proof going from the first step to the second step here? Okay. All right. Naima likes it. Abby likes it. Hun likes it. Wonderful. Wonderful. Then I'm glad it's there. I'm glad it's there. So, okay. Now you know how to find a solution to a linear system of differential equations. You know how to find a solution. Just find an eigenvector of the matrix A and multiply it by e to the lambda t, where lambda is the corresponding eigenvalue of that eigenvector. Okay, so far so good. Are there any questions? All right. Well, we're gonna do another little discussion problem here. May I move to the next page? Is anybody still copying, or are we good? Okay, Nafani's good. All right. And name is good. Wonderful. Wonderful. All right. Okay, well, here's another discussion problem. Let me give you a moment to copy this down. How many recall in differential equations, Math 282, if you've taken it, getting solutions if you have a 2x2 matrix, okay, 2x2 matrix A, getting solutions that are of this form here? How many recall that? Okay, right. All right, so for a linear system of differential equations, the general solution is of that form. Nafani remembers it, Benjamin remembers it, and now you're going to understand why it's true. Okay, so let me give you a moment to copy this down. Let's see, Benjamin has a question. Are these the only non-trivial solutions possible? Yes, they are, Benjamin. Yes. Yes. There would be no other solution to the linear system of differential equations. But I mean, this is the general solution right here. This is the general solution. There are no other solutions around. Okay, no other general solutions. You know, and I mean, of course, we're working with, you know, well, I mean, you can always find sort of, you might, well, yeah, that's right. That's right. Okay, who would like to see the proof of this? Okay, Eleanor's ready. Good, Hung's ready. Okay, may I move to the next page? All right, Abby's good and Nama's good. Okay. Okay, here's the proof. So we're going to take the derivative of this linear combination of eigenfunctions. That's what it is. Now we're A, by the way, A in this problem, it's obvious it's a 2 by 2 matrix. Okay, it's a 2 by 2 matrix. And we're going to take the derivative of this candidate that we think is a solution, this linear combination of two eigenfunctions, right? This v1 times e to the lambda 1t is the first eigenfunction, and v2 times e to the lambda 2t is the second eigenfunction. Let's see what happens. So, of course, we all know that the derivative of a sum of functions is the sum of the derivatives. Well, clearly the derivative of a sum of two vectors is the sum of the derivatives of each vector. The components of the vectors are functions themselves, so the properties of the derivative properties have to follow for the vectors. Well, okay, so let's look here at this first derivative. You have the derivative of c1 times v1 times e to the lambda 1t power. Well, c1 times the vector v1, that's a constant. It can be pulled out front. It can be pulled out front here. And similarly, for the second derivative, we can pull out the vector c2 v2. We can factor it out of the derivative because c2 and vector v2 have just numbers in them. There's they're not functions. There's no t variable in those. Okay, well now what we do is we take the derivative of e to the lambda 1t with respect to t. That just equals lambda 1 times e to the lambda 1t. And I'll take the derivative of e to the lambda 2t. That just equals lambda 2 times e to the lambda 2t power. So far, are we good up to here? Are there any questions? All right, well, So I can reorganize things here, okay? I got C1, I have here on the, like for the first term, I have C1 times the eigenvector V1 times lambda 1. I could write that as C1 times lambda 1 times V1. And then lambda 1 times V1 is A times V1 by virtue of the fact that V1's an eigenvector and lambda 1's the eigenvalue. And I can do similar things. I can do a similar adjustment on the right term here. And so now I end up, this expression on the right, well, this expression on the right, I can factor out the matrix A. I can factor it on the left. The constant doesn't affect, even though there's a C1 and a C2 to the left of the matrix A, that can be, the matrix A can be brought out in front. That's a matrix property. And so I can factor the matrix A on the left side, and what I'm left with is A times the linear combination of eigenfunctions, and that was just equal, that was just how I defined xt to begin with. So it turns out that x prime of t, maybe I'll put it in blue, x prime of t equals a times x of t. It does. And therefore, the linear combination of eigenfunctions is a solution to the linear system of differential equations. And now you know, those of you that have taken differential equations, Math 282, know why that's true. And those of you who are going to take Math 282 differential equations will know why it's true. How many have to take Math 282 perhaps in the future? Okay, Samantha does, okay. Well, and there'll be others of you too who need to take it. I would recommend taking it if you have the time. Sometimes what happens is we'll have students that don't take differential equations, and maybe they got their bachelor's degree, but then they want to go to graduate school, and you know, they need differential equations, and then of course they then come to Montgomery College and take it, and that's fine. But I'm just saying, you know, you all know you can register now, right, for classes. Registration's open. It opened 2 days ago, and you can register for classes. Like if you're taking a class now that's a prerequisite to another class, you can still register for that other class, okay? Even though you haven't satisfied the prerequisite yet, you can still register, okay, for that class. Okay, are there any questions on this? How many think this is pretty cool? Pretty cool. Okay, a lot of you, excellent, excellent. All right, well, I still, thank you, Abby and Eleanor, Catherine, Lewis, excellent, excellent. I still want to do another example. I do need to do another example before class ends, but I'm going to give you 10 minutes of time here just to relax, maybe do, if you want to work a little bit on the assignment that's due Friday, that's fine. So let me stop the recording.